Yeah, again, thank you, Aditi. So another welcome to Bioimaging's North America's talk series on microscopy builds. That's hosted by the Builders Group. So we're going to explore non-obvious but very important connections between industry and open hardware microscopy builds. As you know, we have four really great speakers chosen for their very different perspectives on this topic, and we're going to follow with a panel discussion. So just hold your questions until the end or put them in the chat, as Aditi said. So Jessica Lim, who's co-chairing the session with me, and we're also co-chairs of the Builders Group. Please feel free to reach out to us if you're interested in joining. It'd be wonderful. And if you find the session interesting, we have another event planned on the 21st of May. So please put that in your calendar. We have Gail McConnell, Kevin Dean, Shaylin Mehta, and Alfred Sicking who are speaking in that one on open hardware innovation. So that's just a little shout out to the next one. Okay, so I'll quickly introduce our first speaker. So our first speaker up is Jeremy Graham. So he's had a leading role at Cairn Research for over 20 years, and he very recently started his own company, customScopes, to focus on custom microscopy design and support. So Jeremy is very well known in the community for his innovative contributions to many scientific imaging projects, including the open frame microscope. So I'll hand it over to Jeremy now.
Right, can you see the slides now?
Yes.
Brilliant. Okay, so hi, thanks for the introduction, Gil. I'm Jez Graham, the founder of customScopes, which has been running for about a year and a half now, formerly at Cairn Research. And I'm going to talk to you today briefly about a few projects I've been working on which make use of open source hardware, and the emphasis being on the modularity, the affordability, and the adaptability that I think should be a central theme through open source hardware. So a brief introduction to what my interests are and what I'm doing with customScopes. As Gil mentioned, I'm very heavily involved in the open source microscope platform, working very closely with Imperial College London and still with Cairn Research. And the projects we've been focusing on have been getting microscopes into Africa that can be shipped around the continent and are robust enough for transport and be maintained locally. We've been building microscopes for containment labs where the open source modular nature certainly helps with the long-term support. There's no monolithic unit that needs to be destroyed and removed due to the toxic nature of the labs. Also been working on a few dedicated applications in electrophysiology and cardiac physiology, and building microscopes for startup companies, whereby if they're open source, then when they're ready, they can take the project off in whatever direction they want. In addition to this, I'm very interested in making things cheaper. So I've been working with astronomy, machine vision technology to make predominantly light sources, cameras and filter wheels much more affordable for microscopy, including getting down to the price point where they can serve the amateur microscopy community, which turns out to be quite large. We upgrade existing microscopes to either bring them up to date or to repurpose them for new applications, and do quite a bit of custom build, usually referring to a journal article and helping a biologist to translate some new technique onto their microscope, which will be different probably from what's been published, and working out what's important and how to translate what may have been a breadboard build into a more of a biology-friendly microscope build. So those are things I've been doing. I think it's important to highlight where an open source microscope scores over a traditional and vice versa. So the starting point from a research consultant's point of view is that you're asking more of the researcher. They need to understand and they need to be interested and they need to put some effort into the supporting the system themselves, and consultants like me are there to help them. The support will rely on partnership with the group. Generally, the microscope will be less versatile at point of use, so less suitable to core facilities, but more suited to researchers who have specific requirements. So those are a few sort of caveats, but then the advantages are huge. Many optical systems rely on 4F optics, which doesn't lend itself to a regular microscope. You're not limited by any spectral range. You're not limited by particular tube lenses, detectors, ports. You can build as many illumination and detection ports as you like. Solution will tend to be more compact and cheaper, and it will be sustainable beyond support contracts. So there's no fixed term support contract. There's no reason why the system can't be kept running more or less indefinitely. And I think doing things differently in a modular way encourages innovation, because if you have a monolithic platform, the temptation is to reproduce what people have done before. Whereas if you've got a platform that can be put together in any way you like, then it encourages you to explore new things. So the key aspects that I was focused on in this talk is the modularity. So the system should be built up of discrete building blocks. It should allow as much substitution as possible. You shouldn't be tied to a particular component in a particular place. Everything should be individually swappable. And it needs to be serviceable at a component level rather than a system level. Obviously, the researchers putting more effort in themselves, so it needs to be affordable. The key part of the key to this is they can allocate the budget where they need it. So if they need a fancy objective or a fancy camera, then they can start with that and then potentially save money on other areas and improve them later on. But it means they can get started. There would typically be a very wide price range for each component, ranging from thousands of dollars to building it yourself for tens or hundreds of dollars. And the costs can be spread out over time, so you can get started and then add functionality as grant funding allows and as your needs progress. It also should be adaptable, so it should be repurposable from a simple wide field system to a confocal or a turf rig, single molecule. Wherever possible, we should adopt standard interfaces, which applies to the microscope itself, but also to fitting in with industry standards such as Thor Labs and the standards of the conventional microscope companies, so that it can accommodate Nikon or Evident components as needed. And basically, the idea is to provide a stable base where you can explore new ideas and take the microscope off in different directions. So to reference these sort of ideas, I'm just going to go through 3 examples of projects I've been involved in recently. First one was to build a custom X-spin light sheet on the OpenSpin model. So doing 2 different magnification of detection, dual-sided illumination. This is a project with Imperial College to build a robust microscope for field studies in Africa, and also like an upgrade progression of a rig that has evolved from being very simple to quite bespoke. So starting with the X-spin, obviously the OpenSpin website you'll be familiar with, probably some of you, and it's very comprehensive. It's got lots of parts. It's got lots of CAD files and models, but it's really not modular at all. So the first thing I did to get to grips with building this for the customer who wanted all this flexibility was to take the model and basically to modularize it. So to break everything down into the individual components so that they can be substituted and changed in the future as required. And alongside the modularity, it's also important, if you've got to go to a lab and make a system work, you've got to be careful about the components. So I sort of thought of this idea of a hierarchy. So you have the easiest things are like the catalogue items that will arrive very quickly, relatively affordable and good information online. You've then got core components that you've got to order from the microscope companies or from camera or laser companies. And then you're always ending up searching a few niche suppliers for things that you have to get from somewhere else. And then alongside the commercially available components, you have self-made, but this also has a hierarchy from 3D printing and DIY, which can be done in days and changed on the fly, versus things that are manually machined or laser cut, which turnaround can be probably a few days and relatively straightforward, versus the things that need making on a 4 or 5 axis machine. You need to get those ordered early and get those done professionally and delivered, and try and get those ones right. The other stuff you can adjust as you go along. And here's some of the components from the OpenSpin build. So clearly the chambers and the chamber holder, you need to get them machined on at least 4 axis machine and get that done right. Whereas the modular components and setting up the optical rails It's a combination of either 3D printed or machine parts alongside Thor Labs or equivalent optomechanical parts. So that's the OpenSPIM, and basically just making it a bit more modular so that we can change things. This is the microscope that we built for field studies in Africa. So it's very simple. It has a color monochrome camera, nice 4-channel fluorescence illuminator, a quantitative phase illuminator that was completely open source, built at Imperial, and a robust laptop. And it all fits into a robust carry case and can be shipped around Africa. And this has been shipped around a lot already. It was designed to be fully serviceable by the researcher, use predominantly open source components so they can duplicate it at minimal cost, stable, robust, compact, and affordable, and still maintaining all the adaptability if they want to take it into a different direction and do something interesting with it. And as with everything, always maintain a simple substitution of all components so you're not tied to a specific component. And here's some of the images they've got. They've had that for about 6 months now, and it's been shipped around to lots of different countries. And so far, touch wood, it's not broken. And the final example I was going to talk about is an upgrade route of an open frame microscope that started life as a very simple wide field microscope with basic color illumination, an inexpensive camera. It then got upgraded to do 4 channels simultaneously, then got upgraded to do 4 channels simultaneously and quickly over a large field of view with the kinetics camera. The illumination was not good enough, so we built a critical illuminator with a square fiber, so we can illuminate a quadrant of the camera because the image is split over the 4 channels. Can illuminate a quadrant of the camera with very flat illumination and high intensity, so they can increase the speed. We actually had to develop a new filter set because of the variation in the wavelengths of multimode lasers to ensure that they could have the 4 colors that they needed. Then had to build a custom layer because they decided they wanted a 5th channel for transmitted light with near infrared. And they also wanted dark field. So we designed a RGB dark field, an NR illuminator, and wrote micromanager drivers so they can control the illumination for the transmitted light, and also put dark field into any 3 of the 4 fluorescent color channels in a sequential mode. I didn't get involved in the microfluidics, they're the experts on that. So the group were developing the microfluidics themselves alongside. And as they enhanced the microfluidics, everything moved faster. So the final stage was to box up an Arduino so that we could move Micromanager into sequencing mode so they could get rid of the motion artifacts from the fast moving droplets. So this is all about the adaptability because the microscope's unrecognizable from what started out. And this is the microscope now in its enclosure with advanced microfluidics software and Micromanager running 5-channel imaging. Thank you very much for your attention, and I look forward to maybe any questions at the session at the end.
Great. Thank you very much, Jez. That was wonderful. Yeah, we'll have the questions at the end. So the next speaker up is Jon Daniels. So Jon Daniels has been working at Applied Scientific Instrumentation for 13 years, where he's taken the lead role in developing their light sheet systems, among many other things. So the scientific microscopy community knows him very well as he's a regular attendee and contributor to all the meetings that we attend. So please welcome Jon Daniels. I'm handing it over to you.
I guess it's important to unmute. Yeah, thank you for the invitation to present in this venue. A lot of builders here. We work with a lot of builders, and so I wanted to share a couple case studies. Also, just tell you a little bit about ASI and end with a little bit of discussion around IP, which is something that I find that maybe not everybody has a good awareness of and really impacts how the commercialization of new technologies goes. So ASI is about 35 years old now. We have about 35 employees, and literally like our first product was hooking up a motor to a motorized or to a manual focus knob of a microscope because somebody at the University of Oregon wanted wanted to automate their experiment, and things have progressed since then. And we are pretty well known in the community. Um, Automation is still kind of our bread and butter, but we've done a lot of other things over the years. And this is fascinating to me. Like, for more than 20 years, we've kind of had this mentality that, our goal is to anticipate customer needs and provide cutting edge technology. And this kind of repeats over and over again. And it only does because we're collaborating with people in the builder community. So it's an honor to work with a lot of those kinds of people. So, you know, zooming out and thinking uh, about science, there's a lot of different things that the researchers want. And of course, only a subset of that is actually technically possible. At least once a year, I field a question from somebody that wants something, and I'm like, that's like against the laws of physics. I hope you know that. Sorry, we can't help you there. Um, and then, of this intersection between what's technically possible and what researchers find useful, there's only a subset of that that's readily available. And the goal of both builders and companies like ASI is to expand this bubble of what's readily available into new things. So, with light sheet microscopes in general, but also more generally, I like to kind of think about this on a spectrum between the blue, which is like very high energy, high effort, build your own microscope, optimized for a single purpose. It's going to be hard to replicate, but it's going to be cheap and it's super flexible, and you can do whatever you want. You're going to be building it with Thor Labs components. You're going to be designing your own parts, 3D printing. And then on the far other end of the spectrum is, what a biologist might want as a turnkey instrument. This is going to be a black box. They don't necessarily want to know what's inside. As long as it produces pretty images, it's going to be super expensive, and there will be a lot of compromises that are made to, make this turnkey instrument. And then ASI really, for 30 years, has played in the middle here, where we have modular off-the-shelf components, much like Jez talked about. We've been doing modular microscopes for 20 years now. And what that allows you to do is kind of make something that is available and reproducible. You can build another copy of the system in another lab pretty easily. We're also really big fans of using open source software, Micromanager. And of course, the price point and kind of effort level is somewhere in between the two other ends of the spectrum, right? So I want to share three quick case studies of how we've interacted with the builder community to create new things and help disseminate new technologies. So first is really a story of co-development. So this is the iSPIM or DISPIM. And this started before I joined ASI. Hari Shroff came to ASI, my coworker Gary, and ASI was had just started kind of getting into this modular microscope thing. And he had this idea, hey, I want to build a light sheet microscope on top of an existing inverted frame. And he had this idea, you can have two objectives, one for illumination, one for detection. And this was, a lot of back and forth between NIH and ASI to build these, specific components to implement Hari's idea, right? And there's actually a patent where my colleague Gary, now retired, is actually like on the NIH patent with Hari. So this is a true case of like co-development between the researcher and ASI. ASI, of course, is building all the stuff. NIH, of course, is doing all the testing, and it came with the initial idea. So that has matured over the years, and I'll just give you a couple examples of innovations along the way. So the very first DISPIM had they created the light sheet with a bunch of galvo mirrors that was sitting behind the microscope, very clunky, very hard to build, very hard to align with respect to the microscope. And so ASI, we saw that this was like a pain point, and Gary worked to design this light sheet generator. You can think of it, fiber coupled scanner. So you plug in a single mode fiber and you get a light sheet on the other side, and it has a MEMS mirror inside and lenses and things like that. It's just a little bit bigger than the size of your hand. So this drastically simplified the implementation of the dice BIM, and kind of allowed it to be easier to use and easier to align too. Uh, Here's a picture on the right of an early dice BIM. It was, I look at this now. I mean, it maybe doesn't mean it as much to people who haven't looked at this, but I look at this now and I think, wow, like that's really clunky. And, the adjustments to align the microscope were very, very clunky at first because, you got to start somewhere, right? And you learn along the way. And the modern dice BIM just is so much easier to use and align. And at this point, we've sold more than 100 in some shape or form. So it's been a pretty successful, project. Now, some of those dice BIM or dice BIM-like microscopes that we've sold have been because of the next thing that I'm going to talk about. And that is kind of, pooling customer requests. So dice BIM was still pretty new back in 2016, 2015, and I kept getting questions like, hey, I want to use the dice BIM to image cleared tissue. I have this cleared tissue. It would really benefit from the isotropic resolution of the dice BIM. And I kept telling people, no, you can't do this, but there's not a fundamental reason you couldn't. It's just that there isn't a suitable objective that's out there. And so after telling, enough people this, and in particular at the 2016 neuroscience meeting, there was like 4 people in one day that asked me this question. And but around the corner was another booth of a company that made custom objectives named Special Optics. And so I went and talked with them and I said, hey, could you make us an objective? Like this is clearly something the community needs. And there's some challenges. You have to be a dipping lens. You have to like accommodate lots of different refractive indices, but we were able to overcome that. And in 2017, we had our first prototype objective. And again, it may not mean as much, to you looking at this, but like to me, this looks like really old and clunky. And this black coating didn't survive the aggressive chemicals that it had to be dipped into. We had to come up with something different. But looking back now, in 2025, we came out with our fourth multi-immersion objective. So now we have a lineup of different objectives specifically for this purpose that kind of all came about because people asked for something that didn't yet exist, and we were able to recognize that there was an opportunity to kind of pool requests of individual labs, make a production run of like, these custom optics, they're affordable if you make them in like a batch of 20, but not in a batch of 2. So ASI was able to say, okay, yeah, we're confident we can sell 20 of them. So we're going to like fund a batch of 20 and then sell them one at a time to different researchers. And so that's kind of the model here. And this has been successful, I think, both for ASI as well as for the community that now these objectives exist. And coming in 2026, the production is just starting right now as an objective specifically for expansion. So that's another a second way that we interact with the community. And then a third way or third example is helping to disseminate the benchtop mesospin. So the mesospin project is, I think, coming up on something like 10 years old now. And about 5 or 6 years ago, they started working on a smaller version that's now called the benchtop, and it's kind of like the default mesospin version now. This is an open source project initially started by Fabian Voigt, and now Nikita is kind of pushing this forward. And initially, our interaction with them was around these ASI made stages, and they actually, talked to Fabian sometime. He had a little bit of pain with the ASI stages and helped us figure out something that we could do better, and now that's fixed. And now these ASI stages are on the parts list, and we started getting requests for these. But along the way, we also noticed that Nikita had a bunch of machine parts that he had designed and had modified or made in a local machine shop, and this was kind of a little bit of a bottleneck for people who wanted to build their own mesospin, because then they needed to go find a local machine shop to do this thing. And so what ASI did is all the machine parts now we offer made in our machine shop, and along the way we made some improvements to them in terms of the functionality. So now you can buy all the parts that need to be machined out of aluminum that aren't, just Thorlab's catalog items you can buy from ASI. So in this way, we're kind of helping disseminate this open source project by making it easier for people to buy these parts. And all the designs stay open source. Like, people still can go, use their own machine shop to make these things, but there is a commercial option. Okay, I see I just have 2.5 minutes left, so I'm going to try to make this really quick about the IP. So I'm not a lawyer, but basically a patent, if you understand it, it's important to understand that a patent is the ability to sue to keep other people from making your invention or making money off your invention specifically. And so there's a process. I'm just going to skip that. So as an academic, the main thing you need to know as a patent is you're unlikely to get sued. A patent holder is not going to come after your university because you are infringing on a patent in your academic research. So that's just not a consideration. It's impractical, and the patent holders, especially the big companies, would make a lot of enemies if they tried to sue all the individual universities. Now, as an academic, though, if you have patented or patentable ideas, you probably have to disclose them to your tech transfer office. They're going to take care of filing the patent, and they're going to negotiate any sort of licensing if that patent is granted. And I just want to say here that, if you have a choice not to patent or not, think about if you want to put your ideas in the public domain instead of patenting. And why that is will become clear in just a minute. And that's as simple as, just disclosing it publicly before filing the patent application, puts it in the public domain. So if you're a startup or thinking about making a startup company around your invention, you're also unlikely to be sued until you start making money. But of course, your goal in making a company is to make money, and your competitors would love to stop you as soon as you're kind of taking away their business. So as a company, what you need to make sure you have is called freedom to operate, which is just the assurance that you won't get sued. And you can do that either by licensing or using only ideas in the public domain. So in the microscopy world, and I'll end here, the big four are, they're going to be the best at having a large reach in commercializing some new technology in the microscopy world. But they're only going to do that if they can exclude their tech competitors. So, Olympus Nikon will only kind of adopt a new technology if they can be assured that Evident, Leica, and Zeiss won't be able to. So they want exclusive rights, and if they have exclusive rights, they can do anything they want, including nothing. And so I don't have time to talk more, but I'll just end with saying that, companies like ASI, we only require freedom to operate. We're not like the big four. We will help you commercialize your invention as long as we can be assured that we won't get sued. And with that, I'm out of time, and thanks for your attention.
Thanks. That was great. Maybe we can follow up with some of those discussions in the panel. Okay, so next up is Spencer LaVere Smith. So Spencer is a professor at UC Santa Barbara, where his lab works on neuroscience, optics, and computation. He's also the CEO of Pacific Optica, which specializes in laser scanning multiphoton imaging. So he's well known for advancing large field of view multiphoton imaging in the community, including open source custom optics. And he also runs LabRigger, which a lot of us are very familiar with. So Spencer, over to you.
Thanks so much. Thanks for having me here, Gil. And I echo a lot of the things that John said. Um, I've got a similar Venn diagram at the end that he started with as well. So I think we think similarly about these issues. So yeah, Pacific Optica is the company that we spun out from the lab. I want to talk a little bit about the evolution of microscopy optics and kind of where we are today. So originally, like around the time of Galileo, the first microscopes that people made were completely bespoke. And we still have bespoke microscope builders today, and that's great, but these were really bespoke. Like every single lens was unique to that particular microscope. And those were beautiful pieces of work. But around like 1858, the Royal Microscopical Society decided they needed to lay down some standards so that you could have some interchangeable parts. This is right around the beginning of the Industrial Revolution, and there was a recognition that this would be a good thing to do. And it was. So objective threads were standardized, slide sizes were standardized, and other things, and we still have those standards today. These are the same standards that kind of govern why all of our objectives are basically the same size. So when home builders go and want to build something, for a lot of these low NA components, where you may be relaying an imaging plane or something like that, if you're working below NA of about like 0.4, you've got a lot of options. But once you start getting into higher numerical apertures, there's really only 4 companies in the world. There's 2 in Japan and 2 in Germany that sell these optics. And that's the way it's been for a long time. And there's this architectural lock-in that's happened. And this is it's not just in microscope optics, it happens in all sorts of fields. But basically, it's a specific set of design choices is so foundational that changing them would require re-engineering the entire ecosystem. And so this is an architecture that, when we grab parts off the shelf to build these really innovative imaging systems that we've been talking about, these custom bespoke systems, the bottleneck is always the high NA optics. We've got to grab something off the shelf. And this is an architecture that hasn't really fundamentally shifted in 170 years. So, this has really led to a stagnation. Microscope users put it up with it because they have no choice. The stagnation really slows progress in biomedical research and clinical imaging and advanced manufacturing and more. So we have these small fields of view where we have really nice performance right in the middle of the field of view, but it vignettes really rapidly. And most manufacturers, actually, I don't think any of them, will actually show you how fast it drops off towards the edge of the field of view. It's not until you start imaging beads at the edge of the field of view that you even realize that. It's slow imaging, short working distances. And this is very frustrating for me. I recognized this issue when I was a postdoc, and when I started my lab, I started building optics so that we could do something better. So that effort has evolved into the diesel 2P system, which gives us this really big field of view for multiphoton imaging. It has 2 completely independent beams going into it. I'll talk a bit more about that here in a little bit. The Ventana scan engine, which I'll talk about a little bit as well, which has really solved an engineering trade-off in beam scanning. We found a trick where we can have a non-inertial mechanism for multiplying the beam scan angle. And then we had another problem where we needed to have a really long working distance for 2-photon applications. And most of the objectives that people were using had fairly short working distances and required water immersion, and it was really incompatible with a lot of the types of experiments that people wanted to do. And so we kind of broke some of these rules about what objectives need to look like and the size envelope that they need to fit in. And we're able to create something that was a bit of a hit in ways that I didn't expect. So the key thing that we do is we build the whole system independent of these legacy companies. We don't use anything from Nikon or Zeiss or the big major manufacturers. We've developed a fabless approach for innovative optics, and so we're flexible and can quickly adopt new technology. And we have manufacturing partners in the US and abroad, and honestly, that's like the vast majority of my time at the company is working with these manufacturers to make sure that they can make the things we want. And since we know the optics, we know the user applications, originally I was just open sourcing all this stuff, but it turns out that people, very few labs have the expertise to actually do precision alignment of custom lenses in their lab to build a custom objective. And so I worked as a consultant for a little while to coordinate manufacturing runs. We just realized that there's actually a lot to do, and there's a lot of potential impact we could have. And we've been really pleased at the results so far. So the Diesel 2P has sold into numerous labs across 6 different countries in less than 2 years after publication. The CUSA is sold into 40 labs around the world in less than, I think it's more than that now, less than 2 years after the publication. And this Ventana system I can tell you about has sold into the most demanding labs literally weeks after we even introduced it. So we're happy with the impact that we're having so far. So we can talk a little bit about the Diesel 2P if you're not familiar with it. Basically, it's one of these mesoscopes. So you've got submicron resolution in X and Y. Has a field of view of about 25 square millimeters. We actually went out to a span of 7 millimeters with adaptive optics at the edge to kind of squeeze out a bit more field of view. And what's unique about it is it has 2 completely independent pathways going to the objective. So they're not yoked to each other at all. So you can set the system up in a lot of different ways. And they're combined with polarization, not wavelengths. So you can have the same wavelength in both arms. And do temporal multiplexing. You can look at, a big field of view and a small field of view, or 4 different fields of view, kind of switching between them rapidly, interleaving them. Or you can do random access in one and large field of view in another. And it can be anywhere in that large 25 square millimeters of tissue. I wanted to do this so I could see multiple brain areas at the same time, particularly primary visual cortex and higher visual areas in a mouse. We also want to do some ontogenetics. You can run both wavelengths through the same pathway, but just to kind of, the simpler implementation of this is to run 910 nanometers through one arm and 1040 through the other. And so you can have random access in one and a large field in the other. And we've done things with like using an SLM to make multiple dots and spiral scanning them, and we can reliably activate cells. And we have a whole series of experiments that we were doing with that. The CUSA objective was trying to solve this problem where conventional short working distance water immersion objectives that are typically used for multiphoton imaging in vivo, they can give you nice imaging if everything's right, but you can fall out of that optimum very easily. And sometimes there's even just mechanical issues where you can't get the objective up to the close enough to the plane of focus that you want. And we went back and forth a lot trying to figure out what geometry would work until finally I threw up my hands. I said, let's just get a cone of light in and out of there. Let's move the entire optics, 2 centimeters away, 20 millimeters away from what we want to image. And then we made it really wide, right? We have to because we've got a cone of light coming in and out. But this solved the problem. We also made it air immersion. One of the first things I realized in some of our experiments with custom optics for multiphoton was that air immersion worked. I thought that the spherical aberrations and these other issues would be crippling, but it turns out that it's actually fine. It works really well. And the ergonomic benefits are massive. So if you've got some experiment that's running for many hours, a water interface can shift over time, and you have to get back into the system and realign it. And with air immersion, you just don't have to deal with that at all. It's great. And what I didn't realize is that people who image through Gren lenses and prisms and periscopes and other types of imaging, they also find this useful. You can get neuropixels probes in there. There's lots of applications for having this really long working distance. Here's some specs of it. So it's really optimized for multiphoton, really high performance. It's we also optimized for fairly large scanning angles. So we tried to make it as compatible as we could with conventional microscopes. So that people who use this on Bruker or Zeiss and Olympus and NeuralabWare and other types of imaging systems. But we recognized very quickly that we want to push beyond these scanning angles. So most systems cannot do that full, excuse me, plus or minus 3 degrees scanning angle. And so we have a new version of this, the avocado I'll talk about here. So for most systems, there'll be a 2 millimeter by 2 millimeter field of view.
And if you can go out to plus or minus 5 degrees, you can get a 3 millimeter by 3 millimeter field of view. And we do that with the diesel system or with our Ventana systems. But the CUSA, just on regular microscopes, you can, working in adult ferrets, which have these really thick skulls, that optical window has a lot of biology up and around it, anatomy around it. And it's hard to get objectives down to the cells that they want to image. And other options like the Edmund Optics 20x.6 isn't optimized for multiphoton. And so the CUSA was really enabling for those particular experiments. It also works well in younger ferrets, tree shrew. Somebody wanted to use it for intact imaging in pig retina, which is a common preclinical tool. And this is apparently the first imaging of cochlea in vivo. It has this really complex surgical preparation. We're coming in from the ventral aspect. And other long working distance air objectives they had, like this Nikon 20x.4, wasn't optimized enough for multiphoton and was burning cells. So with the CUSA, they could use much lower power, be much more gentle with the cells. And this is apparently the first functional imaging of hair cell activity in vivo in mice. It also worked for 3-photon, which we didn't design it for. But typical 3-photon microscopes use really high NA objectives, which they don't need to do. You can actually use, this is through 20 millimeters of air with a 0.5 NA objective, and we're able to get really nice images. So this is focusing down through mouse neocortex, third harmonic generations in cyan, and Texas red is the blood vessels. So iterating on this, we did the avocado, which is a little bit higher NA. It's also a little bit higher magnification as well. So the field of view should be smaller, but we optimized for large angle scanning so much that the field of view ends up being basically the same. So you can get about 3 millimeter by 3 millimeter field of view if you're scanning at these high angles. So our point spread functions are smaller. It's basically the same in X and Y, but the axial, you can see a little more of the difference in the axial full width at half max. We get really nice signals. It's diffraction limited over plus or minus 4 degrees scanning, and plus or minus 5 degrees scanning is usable. And then we went to the scan engine. So those are the CUSA was for the objectives, and now we're working on the scan engine. So that we have these optics for the scan. The first thing we needed to do was we needed different scan lens and tube lens optics. So these are, if you're familiar with the threading of Thorlabs components, this is an SM3 threading on that tube lens. So it's a big tube lens. And the Ventana SL, that's a SM2 threading on that bottom aspect. So these are larger, right? If you wanted to higher throughput, higher space bandwidth product, you need to go to larger optics. What we're trying to address is this fact that scan mirrors are inertia limited. So as you go faster, the mirror size gets smaller. And as the mirror size gets smaller, that means you need to magnify the beam more. As you magnify the beam more so that you can overfill your objective, you end up minifying the scan angles by the same factor. So there's this trade-off, and we wanted to avoid that trade-off. And we found a way to double and even just arbitrarily angle multiply or angle amplify by even higher factors. So even with the same optics, you can go much faster. So this is what it looks like inside. So we've got this angle doubling unit, which is basically a relay to another Galvo scanner, sending that back through a polarizing beam splitter, then to the objective. And we need to do, there's a lot of different ways to mess this up. The scan lenses have to be perfect and the tube lens needs to be perfect. But we found ways to do this in a diffraction limited manner. And so this is the Ventana Fast system. These are now turnkey that we sell at the labs. We can do 1 millimeter by 1 millimeter at 4 frames per second with a lot of photons from each individual cell. The Ventana Wide is even larger, so we can go to 3. These are 3 by 3 millimeters. We can actually go up to 3.2 by 3.2 millimeters. And what was really key to get this to work was these, again, custom optics. So the tube lens and scan lens just provide diffraction limited imaging over much larger scan angles. The color lookup table on here is Strel ratio. So what this lets us do is scan a lot of lines very, very quickly.
So the Thor Labs Mesoscope is a beautiful system. It does 12 kilohertz scanning, so 24,000 lines per second. But the scan lines are only about 600 microns wide. So they do 14,400 millimeters scan per second. The Diesel 2P does 24,000 because the resonant axis is 1.5 millimeters. And since there's two beams, it also goes up to 48,000 millimeters, but we'll just talk about a single beam just to make fair comparisons. The Ventana Fast is 40,800 millimeters scan per second. The Ventana Wide is 51,200. And we actually, in this paper we just published, we went up to 76,800 millimeters per second. And so we could actually do a 3.2 millimeter by 3.2 millimeter scanning with 24,000 lines per second, doing a 4x magnification of the scanning. This also works with adaptive optics, so you can increase the range of adaptive optics. And this is Chae-Hong Yu, who's the engineer behind this work. So again, this is the Venn diagram that's similar to John's. Conventional microscopy optics are really limiting our optical design space, and what we're trying to do is push beyond that for new applications. Thank you.
Great. Well, thank you very much. That was absolutely fascinating. Yeah, thanks to you and thanks to all the speakers. That was great. Now we open up for questions. And so feel free either to kind of raise your hand and I'll kind of try to see if people want to ask questions. You can probably just unmute yourself and pipe up, or you can put your questions in the chat. It's up to you. I think I'll kind of lead things off. So I'm like one of the builders in the builders community. I'm very curious to hear people's thoughts on how builders can leverage, or what builders should do if they come up with a new idea, and they're thinking about commercialization, or just dissemination. I mean, all of the panel speakers had like a different route in some way. I mean, either like I know that John's designing his own optics. Jez helps people bring things into, yeah, from thoughts to kind of into the lab. And Jon actually seems to be working with other people, and Hongquan is designing their own. Does anybody have any, if somebody comes to you with an idea, what happens? What happens next? Anybody can, it's not directed to one person. Any thoughts?
I guess I can take a stab. So the first step is just to talk about it and figure out the feasibility. And, if there is serious interest in commercializing, then there needs to be a little bit of thought about the patent landscape. And, you know, can it be, for instance, the Mesospin project, like there's some patent reasons why a company like ASI can't go and just make a version of the Mesospin. But
Hmm.
again, the patent holders aren't going to like go sue your university if you build a mesospin. So ASI can help facilitate you building your own mesospin, but we can't do it for you, like deliver a turnkey product without putting ourselves at risk of being sued.
Right.
Yeah, I would
Tobias.
say, I think John mentioned it in his talk, but my starting point would be to encourage them to publish because it makes life generally, I mean, as John alluded to, it makes life so much easier. They get accredited, they have freedom to operate, and it doesn't remove commercial opportunities in the way that
Hmm.
people think it does. Like particular implementations could be added later on that don't have to be shared, but in the first instance, I'd encourage people to publish.
That's right. And even if there are patent things, restrictions, we're not, when people come and say, hey, I want ASI's help to commercialize an idea, I kind of have to say, well, look, ASI is not a big four. We don't have this huge marketing reach. So part of it is on you to convince other people that this is actually a good idea. And if you have 10 labs that want to build this thing that you've invented, yeah, like ASI can help those 10 labs, kind of get this thing. But we're not going to be the ones to go convince those 10 labs that this is what they should build or get. Whereas the big four operate in a completely different regime, right? Because they
Hmm.
are, they have this huge marketing reach. They decide on something and they'll push it.
Right. Um, Tobias, do you want to unmute yourself?
Hi, everybody. Thank you so much for amazing presentations and nice to see some of the faces behind the companies that I've heard about, but some of us haven't met yet. I have a question around your thoughts or efforts around compatibility between the different systems. So I think most of you mentioned that one of the beauty of building these open systems is that you can address almost any need you might have scientifically. It's very adaptable, but many times it would be nice to actually mix and match certain aspects from different systems, integrating a couple of industrial components and then some specific maybe optics and solutions or a metal frame for the microscope from a company. So specifically on the open frame and also from ASI, there's some really nice scaffolds to put microscopes together, but I understand that's not open source, if I'm not mistaken. So I'm wondering if there are any efforts of making these different frames compatible between, these different commercial ecosystems to be able to make the entire open ecosystem more useful and compatible for the whole community. Because at the moment, you kind of have to decide which way you go. And then even though you're in an open ecosystem, if you don't want to develop a lot yourself, you're still kind of locked into the solutions available already on that system.
As a starting point, I'd say that that Thor Labs has become the de facto standard. So if everybody ensures that they're compatible with Thor Labs, then everything should be able to join up.
Yeah, as I mentioned,
and your threads are all Thor Labs, aren't they? I suppose.
Yeah, the scan optics that we make for the Ventana system, they're SM1, SM2, SM3 threading to help connect. And one of the nice things about modern microscopy optics is having things being infinity corrected. You can relay optical planes, Fourier planes around your system a lot. Where you run into issues for compatibility, a lot of that's just, it's something that you can solve with a CNC part. Right. And at most of the optics that we build in these custom systems, they're pretty forgiving. You can be off by 100 microns and it's not a big deal. And so that makes it somewhat more buildable. But yeah, as far as like if you have a completely novel idea and you're not sure how to fit two modules together, it can take a little bit of fiddling, but it's not hard. But you do need to find the person with the right expertise to figure out how to make those pieces connect together, but it's doable.
Yeah, I just comment to Tobias's point of the, kind of like what's open source and what's not. And I would say that maybe the most important thing is not whether like the full design is open source, but whether you can easily access the CAD models that you need, right? And the optical information needed inside. Like if it's a custom objective, like can you get a black box file at least? If it's a mechanical part, like can you get a detailed drawing of like the tolerances and like the shape of the interface that you need to mate to? And so there's kind of like it's not like black or white, like totally open source or like totally not. There's like, I guess my point is like there's these shades of gray. And although like ASI is like our RAM frame, like we don't publish like the full design of that as much as like the initial open frame did. I would say like the current open frame as well as like the ASI is kind of in the same middle ground where like you can get the right drawings that you need to interface with it, even if like there's not the full, like these are the machining instructions.
Emmanuel, you have your hand up.
Yeah, I would like to make a comment about what Tobias just mentioned about that modular system, which can allow you to do everything all the time. But as user, often they want one microscope which does one thing. Yes, you can be as modular as you want. But for example, in our field, light sheet microscopy, if you make a choice of orientation of your light sheet, then you're kind of stuck in a certain kind of position. So I think there's a view from people like us building microscope DIY, and we make the microscope which can do everything. But the user often end up with one microscope, which is always the one he's going to use all the time for one type of thing. So Can we comment about that? What we would like to do with those things that you can click up together, and what actually the users end up doing with that?
Yeah, no, that's a really good point. And John sort of mentioned this too at the beginning of his talk that there's things that the users want that are not physically possible. There's also engineering trade-offs that users don't necessarily always appreciate what the engineering trade-offs are. They want a bunch of things, and having them all at the same time is not physically possible. And there's also engineering trade-offs that are entailed if you even want them to be switchable or be able to move between them. And we run into this with our multiphoton stuff. I build these multiphoton things, and then I have people approach me almost immediately, say, "Oh yeah, can we pass visible light through this?" And I'm like, "Well, yeah, you can, but it's not going to be optimized for that particular application. We can do that, and we are working on some of that. But that's again, it's not until you actually start putting these things together that you really appreciate those trade-offs. So I agree with you. It's nice to have because most of us we don't want. Usually when we're interested in building something ourselves, we want it to perform amazingly well, right? We want to push the frontier a little bit. And especially in that regime, optimization really matters. And you want to pick your engineering trade-offs for a specific application and not general.
I have a quick question for, I mean, maybe it's all of you, but I was thinking about Hongquan's talk. You said that you switched from going from kind of systems that were using cell phone optics, and then you made a decision at a certain point to kind of build a more professional microscope for robustness purposes. And I was kind of curious about that because a lot of home, like, lab systems, or the ones that aren't that robust. What was the kind of the turning point in that decision? Like, did you run into an issue where the microscopes you were building were failing, or?
Yeah, I think there are two issues. Two issues. One was like assembly was really hard, kind of yield is low. And then the other part is back then getting the data and showing them this principle of detecting malaria parasites with machine learning actually works is more important, and that's the biggest de-risking we need to do. So then led us to use more expensive optics and also components. And then to make things low cost would require a lot of custom engineering. Actually, it would cost a lot of money.
Hmm. Yeah, I mean, because there's this whole now that everybody has 3D printers, it's kind of tempting to try to build your own microscope from scratch, usually. But
Yeah, I think it really depends on the requirements. For example, like the OpenUC2 and also OpenFlexure, those are really successful projects with a lot of reach. And for OpenFlexure, the stage travel does not need to be so big. That's why they can get away with just 3D printed flexure, a very clever design. And for OpenUC2, they with a super modular design, they are really enabling the not only imaging but also teaching of optics.
yeah, no, those are both amazing projects. I guess it's still an open question. I'm sure they have statistics on how often people use their systems for, like, hardcore scientific research versus outreach. I'm not sure. I mean, yeah, but I love both of those projects. They're just amazing. Um, any other
But there
questions?
are trade-offs, right?
Yeah.
And that's, like there's room for all of us in this ecosystem. There's room for like the 3D printed microscope as well as like the super expensive one because there are different needs.
Yeah. Oh, no, totally. Yeah. No, no. I mean, like it would be interesting to know how good a 3D printed microscope can be, or how limited it can be, just because of the kind of the explosion of 3D printing now. It just makes it so that it just seems tempting to 3D print all your Thorlabs parts. Now, I know when I say that, I know that that's not going to work, but it'd be interesting to know why, like, really why not, and at what spatial resolution things start to go wrong, and when you need another company to come in and machine the parts, like ASI or Cairn or Cephla. It seems like there's a certain point when it's like practical to have the 3D printed kind of hack together duct tape system versus a more professional one. And so it's
If I may comment, I mean the 3D printer is very nice, but it's a very specific machine that you need to know how to operate. Because I can tell you people can have 3D printer, they don't know how to calibrate, it's not in a proper room, and their resolution is going to be crap all the time, even though they have a 3D printer. So 3D printer is also a machine you need to know how to operate in order to be able to deliver the part you can actually use in a microscope. Because I've seen some ugly parts
Yeah,
in chambers.
Or hopefully we
Which
see
fail
some
at some
better
point.
designs that are more adjustable. I mean, you can make a lot of use of the flexibility also of the polymer material to make, perfect fit designs that where your tolerance doesn't matter so much and is always going to be centered or has a lot of alignment options inbuilt. I think also, unfortunately, a lot of the parts that we have seen so far, like it becomes more and more common in microscopy, but many of the designs are not very smart. So it can be done a lot better, I think.
Yeah, I've done precision lens mounts with 3D printed parts as kind of one-off things, but when I had those prints made, I haven't made professionally. They're still cheap, but haven't made professionally. The 3D printer that we have in lab, or we have multiple of them, we only use it. We never use it for mounting optics. It's always pretty crude things that we build with it.
Yeah. No, I think that's also my experience.
I would like to ask a questions about, especially after Jon Daniels talks and because we know each other for quite a while, it's the importance of DIY microscopy for new technology. When for us in the light sheet community, the DIY approach has been instrumental to change the attitude of many labs on adopting the technology.
Yeah, definitely. And like, innovations generally come from the DIY sort of community too, right? That's, just kind of the way the academic system works. And there's people on this call that I know who've kind of like developed new technologies, new ideas. And, the first time you build it, you got to build it yourself on a breadboard. That's just the way the world works.
But in the particular thing for us is that there was the OpenSPIM, which was published, and then also you were able to collaborate with the Big Four in order to have freedom to operate, in order to provide the backup of, yes, this should be commercialized as well, which I don't know what your vision on that interaction between you and the Big Four in order to play with a concept which was published in order to open to other field.
Yeah, I guess I wasn't really involved with the OpenSPIM, so I can't comment on that. With the DICE-SPIM, they're basically one of the Big Four wanted to have the DICE-SPIM, and then another of the Big Four said, no, 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 we have a patent that we can stop you. And so in the end, the way that all the patent negotiations shook out is that ASI could sell the DICE-SPIM to anybody except for a major microscope company. So like 3i has a version of the DICE-SPIM, but it isn't, yeah, not one of the Big Four.
Well, that was like written in some sort of legal.
Yeah, that's right. And I mean the patent's now expired, so now anybody could take up the DICE-SPIM. But yeah, that was the negotiation. That was very early in my time at ASI, so like 12, 13 years ago.
Wow, I didn't know you could do that. Just exclude a certain company. Yeah, there's some comments in the chat. So Nico says design for 3D printed parts would make a great course. Like you mean Nico, do you mean like a course that you teach at in university? That would be great. I mean, I would take that course in a second.
Currently in Portugal, there is an open microscopy course led by Benedict Diderich.
Oh, really?
So if you want to join, they have a course on that. I think it's next week or this week. But
Is it?
we have now an open
Good,
microscopy
on
course.
Monday, we're
Really?
organizing with some really great people. Most of the open microscopy community is actually coming together at the course. We have like 13 trainers or something.
Wild. I didn't know about it.
Okay,
Next
it's in
time.
Europe. It's on the other side.
Yeah, not being in North America. But you know what, it'd be great to go to Portugal and learn all that stuff. Just I wish I knew.
I have a question for the audience more. So John mentioned black box files for optics, and we both in my lab and with the company we share Zemax files, and including black box files if we have to. But if it doesn't have to be, then we just share the original Zemax files. But how often, what fraction, or like how common is it for home builders to be fluent in Zemax and actually use that regularly, or some sort of optical design software regularly? I have the impression that a lot of people don't, that they're doing it with pencil and paper and relaying 4Fs and stuff like that. And they're not necessarily diving down to that degree of design, but maybe I'm wrong about that. Or is there other software that people like to use?
Well, I can start off. I just started learning Zemax myself. But that's after 20 years of not using it and doing it as you described. I also got like a lot of use out of something called PhysRay Demo, which is like a 2D optics program, which just doesn't let you do any of the stuff that Zemax does. But I actually agree. I don't think, mind you, I do collaborate with labs in the UK, and pretty much all of them have some Zemax license.
Okay.
Yeah, but it took me like coming from the life sciences to the optics side, it took me almost forever just because it's expensive, so you can't really. I mean, I remember downloading it a few times, and then I have that week-long time to learn how to use it, and it's like, oh, I don't know how to use it yet. Yeah.
Yeah, I kind of want to second that. I have a number of people in my direct environment who use it very intensively, I would say, but that's a low number. I think indeed the cost is the prohibitive aspect here, and it would be so awesome if there would be more accessible software that would do these things. And I'm kind of hoping for someone with the right interests and the current AI coding accessories that speed up everything like lightning fast, that we may get something that, that we as a community could, like an open source version that would be really, this is really good and has a good foundation, and I want to start using that. I would love to see that, or would love to hear about it.
Yeah, I agree. I mean, there's open source, on GitHub, there's projects that people have started where they're making something just to do some ray tracing or look at some EM wave analysis. And we do some of our own like little things in the lab when you need for a small application. But to make something that more people would share, I don't know. It's just that there's this huge merger, right? So now Code 5 and Zemax are owned by the same company. And so I think there's an opportunity for another company to kind of come forward and say, here's some software. It's like 1/10 the price, and it doesn't try to do everything, but it works for this imaging and microscopy communities. I agree with you that I hope somebody else comes along, but in the meantime, Zemax is sort of the lowest common denominator that like Code 5 doesn't have these black box files and stuff like that, right? So even though their optimizers are better, it's a little bit messy. I wish it was better solutions.
I mean, it seems to be being kind of a fluke that Zemax became the dominant company there, because like when you go back like 20 years, it was just a new kid on the block, and there were all these other packages, and it just kind of consolidated on Zemax, and that has become a huge entry barrier. So yeah, no, so this Kraken optical simulator, it sounds great. Would be, I think what we really need is to have something that a whole community would consolidate upon. Otherwise, it's going to be a little bit this here and there, and I don't know how. You would be someone who could drive that.
And the barrier to entry is how difficult it is to start with. I mean, Gil, you were saying you've tried a few times for a week. You know, in a week you can't even simulate one lens, or maybe an achromatic doublet or something. I mean, you can take a pre-created lens, but trying to do it yourself from scratch is really hard.
Yeah,
I find CMAX such a hard, and because I only ever fiddle with it once every 3 years,
yeah.
when I sit down, I can never remember how I did what I did before.
Yeah, there's a whole vocabulary and codes for setting up the merit function and whatnot. I teach it in my optics class. We spend one of the first labs is we build like a 4F in like a laser scanning system for a microscopy, and we start with paraxial lenses and we start putting in stock lenses and look at spot diagrams and whatnot. But it is, yeah, the learning curve's rough, and it keeps kind of changing too. We have to rewrite the demo about every year because they change the interface around enough that it looks unrecognizable from the screenshots we had before. But yeah, I agree. There's room for improvement. Yeah.
Yeah, it also seems like just as a first time user, it seems like it's built on some very old bones.
Oh
You
yeah.
can't
Totally.
comment anything, or the comments are sometimes used as the parameter for like, okay, yeah, we're looking it's like what are we doing? So obviously amazingly powerful and successful and valuable, but it's like yeah, it's a bit shocking sometimes.
It could be done better. Yeah.
Yeah. So the one thing that ZMAX is really nice about is that it are the black box capability, right? So that allows us to share something that people can use for simulation without giving away the entire recipe that that somebody in China could go and copy and undersell us.
Yeah,
Yeah.
that's true. That is cool.
And one comment going back to what Tobias said about interchangeability. So I expect a lot of people here know this, but Nikon and Olympus, the Japanese companies, those optics, like the objectives, are fully corrected internally. And so you can mix and match those with tube lenses. Zeiss and Leica, the German companies, are not. You kind of have to use the objective with that company's tube lens at the right spacing if you want the full performance. And then the ASI objectives, and I assume Spencer's too, like we've kind of done all the correction in the optics themselves. And then the other comment, again, on this like mixing and matching components, we haven't really talked about the software aspect, and that's where Micromanager has really been a game changer to allow people to, combine different cameras, different light sources, including using like, the big four stands, and kind of like have it all run in one software without having to write the software entirely from scratch, but then it's open source and extensible. So kudos to, Nico among others for pushing that forward.
So that brings up some of the challenges in two photon imaging, especially with multiplexing, is high bandwidth, like really high speed data acquisition. And this also runs into some miniaturized stuff like the UCLA Miniscope program. Daniel's done a great job with the electronics, but it's still like multiple chips on a board. I've got a colleague here, and he and I have been working on ideas that could be impactful for like ASICs for head-mounted microscopes, where you'd integrate more of this onto one chip. So it'd be much easier for people just to buy, an imager and attach to a chip, or just buy like one chip and all you need is a connector for data in and out. And also trying to develop more flexible kind of offline. One of the bottlenecks with high-speed data acquisition is everybody wants to do it on a card that sits inside the computer. And the overhead of that is crippling. And so we'd like to offload that to a device that would do all the high-speed data acquisition and then have a lower bandwidth connection to the computer for kind of live view, but then all the data would be saved and streamed and kept. And then you can do things at gigahertz rates without having to worry about the operating system hogging resources or dropping frames or something like that. So maybe that's too big of a question for this group. But if anybody's interested in that kind of stuff and you want to email me thoughts, I would love to hear, because whatever we make, we want to make it useful to the broadest audience we can.
Yeah, I think that's actually really cool that it kind of also touches on something we're dealing with in all other microscopes, and that is there is like hardware synchronization of all the different components. And the way that has been done traditionally is all with NI boards, and that's probably what you also are using for data acquisition there. And so National Instruments is one of these other things that has kind of become a de facto standard that is not really innovating, and at least from what I see, and all these things become more and more of a bottleneck for all of us, and we're finding like low cost ways around it by having little Arduinos or teensy microcontrollers, and there's all kinds of cool stuff you can do there. And in your case, you would need a much more higher end kind of microcontroller version of that to do the digital and analog I/O and keep that away from the computer. So I think it's a super interesting topic, and there's a lot. It's a broad one.
Yeah,
Well, maybe
the idea to make it platform agnostic, so it could work with Micromanager, it could work with whatever custom software you make, and that would be the benefit to it. One of the benefits to it.
I mean, I mean, we're talking about 4Labs and National Instrument, but I'm not really sure that they reach all the microscope builders. I have no clue about what's the situation in Asia, China, and things with what is their default companies to provide parts. We're talking about Europe and America, where we have kind of the same similar platform, but I'm not really sure about what the situation within. I mean, Australia, they probably have the same, but I don't know about Asia. I mean, it's a question about who is their de facto and default manufacturer there.
I'm really jealous of Hongquan because he seems to have a much better grasp of that than I do.
Yeah.
Well, for us, we've been mostly just using Tinsei in the custom PCB. Because now the Tinsei, they are so powerful, they run at 600 megahertz, and there seem to be enough IOs.
But the parts you get, you still use 4Labs parts, do you?
Say it again.
Do you use 4Labs and National Instruments, or you have your own?
We use Star Labs. I personally haven't used much because we found microcontroller can do a lot of what we need. But Star Labs is what we've been using.
The other option is
so old-fashioned and expensive that I think for most people in outside the US and Europe, that's not really an option, because at the one hand you pay a huge amount and then you're sort of locked into their more or less LabVIEW dominated ecosystem that is exactly what we're trying to get away from. So I have not worked with that since I have my independent lab.
and the LabVIEW is horrible. As soon as you as soon as you design it, you move on. A year later, you come back to it, you can't remember anything.
Yeah.
But the other thing, the other thing which I've been using a bit, which I really like, are Pi Picos. So this is one with a network socket on it as well, so you can talk to it over the network. And they've got these the programmable. Well, I can't remember what they're called, but they've got hardware programmable stuff for digital I/O, which works super fast. You can get it putting out signals at 100 kilohertz trivially. Forever,
What are those? What can you? Yeah.
The Pi Pico. It's got these. It's got two blocks of programmable digital I/O, which are completely separate from the CPU. So you pre-program them, and they can do DMA. So you can set up an array in memory, and then you can access that, and they can do loops and all those kind of things as a separate thing away from the processor. So it doesn't matter what the processor is doing. And then the Pi Pico itself has got 2 ARM cores or 2 RISC-V cores. The new ones have got both, but you can only run either the ARM core or the RISC-V core at once. I've not actually used the RISC-V.
We also use the Red Pitaya single board computer that has an FPGA chip. So if you need some serious sort of real-time processing, I mean the limitation is that it only works at 50 megahertz frequency, the clock. So it's not suitable for all applications, but it can do a lot beyond, let's say, regular microcontrollers and Raspberry Pis or whatever.
And it's got
solutions.
high quality DACs on them, or some of them do anyway. So you've
Yeah,
got a
they do
couple of
have
high
really good
quality
DACs. Yeah, so that's really important.
input and output in analog.
They don't have a lot of channels, but now there is a stackable version available that we're playing around with.
Oh, right.
And the DACs are like you can choose the voltage range 0 to 5, 0 to 10. So those are all.
They have two voltage ranges. So I think it's, if I'm not mistaken, it's 0 to 1 or 0 to 5 or something. It's not a lot of options, but
I think they run at 3.3 volts, and I think it's minus 1.8 to plus 1.8 volts. So I think you can do 0 to plus 1.88 volts.
Yeah, I think those.
So they're jumpers, so you can change it even. So you can just select physically like which range you want for which input or output.
We had to build a little analog amplifier, low mag, because you can't even buy a commercial analog amplifier which will do fast, high quality amplification of only 5 times. So if you want to go 0 to 2 volts to 0 to 10 volts or something.
Yes. Yeah, so I don't know. I think, putting designs for these kind of things online. I mean, yeah, I would love that. These are kind of like technical hurdles because, like we're not all electrical engineers and know how to do these kind of things. And so then that is kind of where you get stuck on those kind of projects and then, let's just get an NI board and do it. Or Austin Blanco's trigger scope.
That could be like something that the builders group maybe takes on as a bit of we could post that on BINA's website, maybe as a contribution, because I think we all kind of agree it would be nice to have.
Yeah. Hey, thank you everyone for the great seminar, actually.
What are you suggesting we post, Gil? Sorry, I don't quite understand.
No, it's just like this long discussion about replacing National Instrument parts with microcontrollers. And then Nico saying that, well, how do we interface those microcontrollers successfully to analog sources and like getting the ranges right? And you popped up a nice little board, just you happen to have it sitting at the desk. And I was like, that like you had to design that, and that's something that took time. But be good to have that we're all like, it seems like in the event, like something that we could maybe do or
I gotta go.
Yeah, it's true. We're over time, actually. It's true.
Thank you, everyone. Great.
Okay, so wonderful session, everybody. I think this will all be posted online, and thanks to our 4 speakers. If anybody has any closing remarks,
I just wanted to add regarding the DAC card and National Instrument. I recently found this board, like it's called STM board. You can run up to 160 megahertz. And the nice thing is that you can build up like any other type of controller. Like in this case, I'm making like a 16-bit small daughter board that you can easily stack them on top of the others like this. And then you have like a very high quality data microcontroller, like ADC board.
Sounds great.
Yeah, so if somebody has a question on ADC,
you know what? I'll just I'll set up a builders group session where we can maybe discuss this in more detail, and I'll send out an email to everyone. That would be great. Like it'd be really fun to talk about, and I mean everybody has the same. It's amazing that different solutions are out there, and they all seem to be really good. And of course, it's wonderful. I'm still using Arduinos. So I can up my game a little bit. All right. Okay.
Thank you.
Again, thanks everyone. That was a great discussion, and we'll figure out a way of continuing this. And remember, we have another one of these sessions in May. I think it's the 21st. And this whole thing will be posted online. So it's wonderful that we got some discussion going. And big thanks to our speakers. All those talks were wonderful. And I'm looking forward to continuing on these topics with everyone. All right. Bye-bye, everybody.
Thank you. Bye.
Thanks, everybody.
Bye.
Thanks a lot.